So up until this point, when we're finding an antiderivative, we're doing some sort of integration. It's been a straightforward application of some kind of anti-differentiation rule, right? Like, for example, I'm just applying the power rule or something like that. However, a lot of times, like the integrand came from the chain rule. There was a composite function. So in order to integrate that, we're going to do it by substitution. If you take a look at our first objective, we're going to use a change of variables to evaluate indefinite and definite integrals, all right? And then the second one, just to cap out this whole entire unit, we're going to see a couple of tricks that we can use to simplify the integration process, assuming that the function has some kind of symmetry, right? So the second objective, we use symmetry as an aid in integration. So let's warm up. Find the derivative of h of x is equal to the square root of x squared plus x. Wait, why are we taking the derivative? Well, notice that this is a composite function, right? And so what we're learning to do in this lesson is to take the antiderivative of something that originally came from the chain rule, okay? And that's what we have to apply on this one. So let's rewrite our function so that it's to some rational power, and then I can leapfrog that power down, of course, and then apply the chain rule. So I would have 1/2 x squared plus x to the negative 1/2 power, and then multiply it times the derivative of the interior function there, which is a 2x plus 1. Let's clean this thing up, bring this x squared plus x down to the bottom for a positive exponent, make it look real pretty. Okay, so notice that we have this x squared plus x, which was the original interior function. It's part of our answer here, right? Not only that, we have its derivative. Where's its derivative? Its derivative is the 2x plus 1. That's right here on the top. And the exterior function, the original function really, that all of this was stuck inside, is just the square root of x, right? Okay, so what we're trying to do in this particular lesson is work this whole process backwards, that this is my integrand, and I'm trying to find the antiderivative of, and I want to work this thing backwards. When I look at it like this, it's pretty tough to see. It's pretty tough to be able to just follow these steps backwards. So what we're going to do is we're going to change some variables, as we'll see here in just a little bit. We're going to do a substitution. It makes it so much easier. So let's recap the chain rule. If y is equal to f of u is a differentiable function of u. So u is our interior function. And that interior function was some sort of function of x, g of x. Then we have the composite function y is equal to g of, or oh, that says f composed with g of x. It's also a differentiable function of x. And then here's the Leibniz notation, dy dx is equal to dy du times du dx. This is saying the derivative of the exterior function with respect to the interior times the derivative of the interior with respect to x, right? And here's how we usually write it in terms of some sort of prime notation. It's the derivative of the exterior again with respect to the interior multiplied times the derivative of the interior function. So again, substitution. This whole entire lesson is about trying to work this process backwards. We have our equation. I'm trying to find the antiderivative, and it came from the chain rule, right? So here is that all played out here. I want to find the antiderivative of h prime of x is equal to, and again, I can see this rational function here. And what I want to notice about this is that I have some sort of interior function inside of the square root, this x squared plus x. But not only that, I want to notice that its derivative is also part of my original function here, this 2x plus 1, right? And you can see it mapped out here with our interior function and the derivative of our interior function. And it must have come from this square root of x function as the exterior function. So I'm going to work that chain rule backwards. Here is the chain rule. And so to work that thing backwards, it should just be f composed with g of x, and then don't forget your plus c as your constant of integration. Once again, like, it's tough to see this without doing this technique that we're about to talk about called substitution. All right, yeah, you want to go back and substitute that in. And so our first objective here, major objective for this entire lesson, is to be able to use that change of variables to evaluate both indefinite and definite integrals. We're going to see that process in the next video.